Hello, everyone. Welcome back to Kids Python Challenge. Okay, so let's continue where we were from where we were last time. So what were we doing? Last time we did the check. We wanted to find the happy numbers and the happy rate, and we went all the way up to say 10,000 or 100,000. And the original way, naive method wasn't so fast. So by using the new way, which uses set, keeping the record of set of unhappy numbers, we can do it faster. And we kind of measure time and visualize by comparing the two graphs. Okay, so let's look back the code. So open ex4 and connect. And so we did, using the first method, we drew a graph like this in red, and which is kind of slow. It takes time. But using the second method, green, we could do it much faster. So for example, typical example is that in case of the first, it took about, say, for 1 million, it took about 18 seconds. Whereas the second method, for 1 million, it took only, say, 3 seconds. So it's a big difference. And the difference is larger as we go further into larger number or onto larger numbers. Okay, I hope you remember. So homework, how far can we go with is happy set? Actually, it depends on with the 200 million, it already takes 35 seconds. So let's redefine unhappy set version and see how long it takes to go to, say, 20 million. Okay, let's see. For example, let's copy this part, open here, paste it here, go back one by one tab, untab, shift tab, and say ulim, when ulim is 20 million, okay, we need to use the is happy set. Okay, that's it. Okay, and then say, let's do, we need this too. Okay. Okay, so maybe we should have used this code. Oh, no, not this code, but this code. And using the, okay, sorry. So we should have used this code. And ulim list is like only 200 and 500, 50 million. Maybe it takes a long time to do, but we can try with that. So, okay, maybe we don't need it. So instead of adding, just we can do it. Okay. The trouble is we forgot to import the time package. Okay, so import time. Okay, so maybe let it do, and let's go on to next slide. Okay, so today's work. Okay, today's topic is prime numbers again. Okay, so let's see, let's remember what we did in prime number find discovery in lesson 25. Okay, so before going back to lesson 25, it was like this. Yeah, you remember this code. So let's do our work again and remember how we did it. But before that, let's see how our program is running. Oh, it's still running. So let's stop it. Okay, for 20 million, it took over 1 minute. 74 seconds. So we can see that it takes a long time. Okay, maybe you can do it if you like that. Maybe so we found that 10 million is about a reasonable time limit. Okay, so let's go on to today's work. So let's make a text box here to write that the topic is about prime numbers again. Okay, so you remember how we found prime numbers? So prime number is defined as those numbers that have the divisors or factors, two divisors, exactly two divisors, exactly two factors. So what we did was, for example, if we want to find prime numbers up to 30, maybe let's see, for I in range starting from say 2 to 31, if so divs, so let's define divs factors. Divs is fine. Last time we used factors, but maybe define divs. For n, the define to return list of factors is defined as for I in range 1 to n, if n percent I equals 0, meaning I is a divisor or factor. So prepare a print div list as empty, and if so, the divisor div list append I, and then return L. Okay, so this will give the list of the function to return list of divisors, factors. And so the way is, if length of divs of I, maybe we can use n here. Of course, we can use I, but let's use if divs, this is 2, okay, then print n. So this will print, sorry, divs, define divs, Boolean has length. I see, okay. This should stop here, okay. The divs returns list, and we want to apply len function to list, and if it is 2, it returns the numbers. Okay, something is wrong. What's wrong? Okay, DL. Okay, this should be D. Okay, so no. Starting from 1 to n plus 1. Okay, this should be. These are some strange things. So if we print out only primes, these are primes up to 30. Okay, so that's what we did last time. Okay, make a list of prime numbers up to 30. So maybe if you want to answer this, prim L equals 0, maybe prim L1. And if so, prim L1 append n, and lastly print prim L1. This will give the prime list of primes up to 30. Okay, we break as soon as the div list is longer than 2. Maybe a little faster way is to return. So instead of doing this, maybe for this purpose only, we can break as soon as longer or equal to, if longer than 2, return DL. This will make it a little faster, actually, and the result is the same. Okay, let's do, because today we are going to do faster way to find prime numbers, which is called Sieve of Eratosthenes. Wrong, very difficult pronunciation for me. A Sieve of Eratosthenes, and compare the time just like that we did last time. So let's first implement Sieve of Eratosthenes. So prepare a list of zeros up to 30. Okay, the second method is this. So let's see that. Let's prepare a list of sieves, numbers, zeros up to 30. So you remember we can do this way? Yeah. By doing this, we can prepare a list of, let's check that. So this is just zeros 30 times, okay? For each n, set 1 to multiples of m. This is the concept, okay? So the idea is like this. For each, let's see. Okay, so this is not prime number, so forget about 1. So starting from 2, if 2 is still empty, right? 0. Okay. In that case, starting from the multiple of 4, just add 1 to multiple of 2's, starting from. Okay. And then check the next one. Okay. 3. Okay, this is empty too. So starting from 3, check, add 1 to multiples 3. This is already 1, but I don't care. So 9, 12, 15, and like this. 4 is already 1, so let's skip it. Okay. If 5, okay, add 2, a multiple of 5, and like this, continue this. So the idea can be implemented as, okay. So basically, for if the, say, m, if NL, no, m is 0, then starting from P equals m plus m, which is the first multiple of m, and then so let's define the upper limit to 30, and let's change this to upper limit. And for, say, I, j, wow, we can do it just by while. While p is less than ulimit, less than or equal to ulimit. So maybe we can set NL p to 1, okay? And do it. So when m is 2, it is just doing the multiple of 2. All the even numbers starting from 4 to 1. And then we do it by, for m in range, starting from 2 to ulim. Okay? Very simple. Okay? If it is marked, we do nothing. Okay, let's see how this works. Okay, we forgot to increment. Sorry. After this, we increment what's wrong? m equals 0. I see. I forgot to increment p by m. Yeah, that's right. Okay. P equals okay. It should be less than. Sorry. Okay. Okay. So finished. So let's check the numbers. Okay. So let's check the list. So if you have it, it's like this. We don't see anything here. Actually, the number is 0 for only those positions as in primes. Okay, let's check that. Starting from 2 to ulimit, if NL I equals 0, print I. Okay, that's it. So this will pick up only the prime numbers. Okay, this is the essence of Sieve of Eratosthenes. Okay, so instead of printing, maybe we can do as set prim list 2 equals empty, and instead of printing, we can write prim L2 append I. Okay, and then lastly print prim L2. Good. So this is how we can find the prime numbers using Sieve of Eratosthenes. Prepare a list of zeros up to 30. For each n, set 1 to multiples of m starting from the next, and pick up those untouched places. Okay, homework. Try up to 100 and check the results. I think it's quite simple. This is the pattern. So try, instead of 30, try 400 and see the result. Okay, that's all for today. Hope you'll come back next time. Bye-bye.